if the overall molecule is polar, then it means that one side of the molecule will generally be more positive and one side of the molecule will be more negative. But now we're talking about the entire molecule, not just the bonds inside of it. So we still use the idea of polarity with the bonds, but I'm going to show you how we can add those up to find polarity for the entire molecule. So in this case, we would say, all right, we look at each individual bond, and we say, okay, it's an OH bond. We know an OH bond is polar. Partial positive on the hydrogen, partial negative on the oxygen. So you can write in those partial charges for each bond. And then another way that we can think of polarity, that we did think of polarity in chapter 9, is as a vector. That is something with a quantity that has a magnitude and a direction. So we have a magnitude, which is how much separation of charge is there, but we also have a direction, because we know, like, okay, the electrons are kind of going this direction and congregating over here. So the way we drew that in chapter 9 is by making kind of a little plus sign and then extending the arrow in the direction of electron travel or electron pull, so going from positive to negative. And the same thing on the other side because we have another polar bond there. And I mean, I drew those the best I could, but they should technically be the exact same length because we have the same magnitude of electronegativity difference between an H and an O or an H and an O. All right. So now if we want to find the overall polarity of that molecule, we have to add those vectors together to get the overall polarity vector for the molecule. So how do we add vectors together? Come on, remember back to your physics. Yeah, you just kind of stack them head to tail is the easiest way. So imagine that they're like directions, like you're taking a path in various ways, and like figure out where you end up. So in this case, we would say, just for demonstration purposes, rather than redraw them, I'm going to move them around on the computer so we can really see it. But we're basically saying, okay, we're going to take this one. Try that again. One more time, and then we'll just give up. Okay, we'll give up. So let's just draw it. So we're going to redraw our vectors over here. So I'll draw that first one that goes like this. And then I stack the second one starting at the head of this one, going the same direction with the same magnitude. Okay, so it's like we're taking a path that's directed by these vectors. So then the sum of the two vectors goes from the tail of the first one to the head of the last one. And we call that our overall molecular dipole. So the overall polarity of the molecule is given by the sum of the vectors for the polarities for the individual bonds. Now, the way we're going to work on this, and the way the book kind of talks about it in chapter 10, we're not going to do the actual math of adding up these vectors based on their components. That's not necessary in most cases. What we want to know is, does the molecule overall have a dipole moment? Is it polar overall or not? So if you end up with a non-zero overall dipole, then we can say, yes, this molecule is polar. So we would say that, yes, water is polar. It has a dipole moment. And its overall dipole is in this direction, going from the bottom to the top of the way that we've drawn it. So down where the hydrogens are, up toward where the oxygen is. And what that tells us that is if we encounter a water molecule, or if another molecule encounters a water molecule, then it's going to have basically a more negative side near the oxygen and a more positive side down near the hydrogens. And all of that is pretty intuitive based on what we know about the water molecule. We're not like finding out anything new. What's nice about this method, though, is we can use it on other molecules where it may not be so obvious what's going on. So let's try a couple more. Let's take a look at carbon dioxide and sulfur dioxide. two different molecules. Carbon dioxide structure looks like this. For the geometry here, we don't have any lone pairs on the central atom, so the electron geometry and the molecular geometry are going to be the same. We would say there are two groups on the central atom, because multiple bonds still just count as one group. There's two things coming off of that central atom. So what kind of a geometry do we call that? Linear. And what's the bond angles? 180 degrees, yeah. So we got a linear structure there. Okay, so let's do that same analysis in terms of polarity. So we're going to look at each CO bond. Is there an electronegativity difference between carbon and oxygen? There is. It's pretty significant. It's about 1. So that means that we can draw those dipole vectors as going from the carbon to the oxygen, the electrons being pulled out toward the oxygen, and then the same thing on the other side. And those bonds are identical, so we would expect the same magnitude. So we should draw those bonds the same length. All right, what is the sum of those two vectors? It's 0, because we're going a certain amount in one direction, and then we're going back the same amount in the other direction, so we end up where we started. So the sum of the two bond vectors is 0, and so we would say that carbon dioxide's dipole is 0, and so therefore this molecule is nonpolar. So even though it is made up of polar bonds, the bonds sum to 0, or the polarity vectors sum to 0, so we end up with no overall dipole moment. And let's see how that's different in SO2. So there's a couple different ways we can draw a Lewis structure for SO2, depending on whether or not we want to minimize formal charge. This is the way it's most commonly drawn because even though it does not actually minimize formal charge, so we've got a negative charge here and a positive charge here. If we did another double bond between the S and the O, then we would minimize formal charge. But what's the geometry here? How many groups on that central atom? 3 groups. So what kind of electron geometry is that? Remember what it's called? Trigonal planar. Good. So we can draw, if we include the electrons, we would draw like this. Okay. And then the actual molecular geometry, we would say is bent. And this bond angle we would expect to be maybe a little less than 120 degrees. Okay, so now this molecule gives us a little bit more complications when we're trying to figure out the polarity. Noah, is there an electronegativity difference between sulfur and oxygen? There is, yeah. Remember those second row, N, O, and F have really the highest electronegativities. So pretty much anything bound with one of those is going to be polar. So yes, so we've got 2 SO bonds. Should we draw those bond vectors, those polarity vectors, the same length? Do they have the same magnitude? Or do they have different magnitudes? In other words, are those bonds, we drew one as a double and one as a single. Are they actually different or are they equivalent? Because if they're actually different, the single bond should be longer than the double bond. Is that what's going on here or not? What do you think? Are those bonds the same or not? We have to know this to be able to draw the bond vectors. If they're not the same, then the vectors are going to be different. You're saying they're not the same? Why? Because you got a double bond and a single bond. Double bond is shorter than a single bond. Okay. Agree? Disagree? So the way we drew this, that's correct. But if we think about the actual molecule, what are we forgetting here? Yeah, that we have resonance in a structure like this. So even though we randomly picked one version of this to draw, we have to always be looking out for resonance structures. And in this case, we see a resonance structure like this. And those resonance structures, are they equally contributing to the overall structure, or is one better than the other? What do you think? Those two that I just drew. They're equal, yeah. There's not like one that has fewer formal charges or one that doesn't have an octet or whatever. So they're equal. So that means that the actual real structure is going to have equivalent SO bonds. Each bond is going to be about 1.5 of a bond length compared to the other, or compared to a single bond or a double bond. So it's going to be right in between. So that means that when we draw our polarity vectors, we should actually draw them the same. So we have equivalent vectors going here. Whoops, except I drew them backwards. Still thinking about water. Going like that and like that. Or we've got a partial negative on the oxygens and a partial positive on the sulfur. So we add those up and we get an overall vector that's going kind of from the top to the bottom. So if we go this way and then this way, we end up with that. And so SO2 ends up being polar in the same way that water does. And this is why we talk about molecular polarity now, because until we know the actual structure in 3 dimensions, we can't make that assumption. SO2 and CO2, when we first write down the Lewis structure and we're just using straight or 90-degree bonds, there's no way of really judging whether or not those are polar. Once we know the actual shape, which one is linear and one is bent, then we can add up the vectors and find the polarity. Right? So when you're looking for overall molecular polarity, you have to know the molecular geometry first. Okay. So now you try one. Let's do 2 different ones. We'll do PF3 and PF5. So draw Lewis structures, work together if you want. Find the molecular geometry, and look at the polarities, the bond vectors. See if they're polar overall or not. All right, did you get a chance to draw some of these? So hopefully, we're going to skip a couple of the basic steps, but hopefully you found that PF3 ends up being a trigonal pyramidal shape because of the lone pair. I'm going to exaggerate the pyramid a little bit just for the purposes of this. Something like that. And so what should those bond angles be? I might have to look back on that one. About 110, just under 110 probably because of the lone pair. Okay, so now let's figure out the polarity. Is there an electronegativity difference between P and F? Yeah. So we can draw our polarity vectors like this. Okay. Now, since this one's kind of more in 3 dimensions, because we've got this trigonal pyramid, this pyramidal shape, we have to maybe do a little bit better job of thinking in 3 dimensions and trying to figure out how we're going to add these vectors up, because it's not as easy to just draw them and just say, okay, we go here and then here. So let's think about this. If we are going, remember that we don't need to specifically add up the vectors like to get quantitative results. All we need to do is decide if these vectors add up, is there an imbalance of electron density? That is, do they mostly point toward the same direction or not? So in this case, do they or not? Yeah. They mostly do, right? They're all kind of pointing down. So no matter how we add them up, we're just going to kind of be like this, and then this, and then that, or something. They're all going to end up pointing down. And what actually ends up happening if you do add them up is because they're in kind of a triangle, the horizontal components of those vectors all cancel each other out, and so it only points down, like kind of right down into the middle of that pyramid. So our overall bond vector is going to be like that, and we would say that this is polar. Yes, exactly. So if you see all the bonds going kind of in the same direction, all the vectors going in the same direction, you can assume that it's polar. And the negative side is whatever side they're all going to. Yep. Where it can sometimes get a little bit tricky is like in this next one, PF5. What kind of a structure is that? Yeah. So this one's going to be trigonal bipyramidal. Like this. Okay, so now we've got all these bonds, 5 of them, and we have to decide if they add up to overall positive or negative charge. And this is where it can get where we have to be really careful. So a couple of them are, I think, relatively clear. So the fact that like these two, the axial ones, are going to cancel each other out. You can see that, right? So then the question is, do the middle ones cancel each other out or not? The way that we've drawn it, it kind of looks like they don't, because it looks like there would be 2 bond vectors on one side and one on the other. But they actually do. And let me show you why that is. If we have, let's just kind of draw a generic trigonal planar shape. Because that's really what this is if we're looking down from the top or the bottom. We have a trigonal planar shape. So if we add up those 3 bond vectors, if we imagine like this, and like that, right? What we've got is, start there, go there, and then back to here. So we do actually end up canceling out those 3 bond vectors. So this molecule would not have a dipole. Would not be polar. So because these things can be kind of difficult to visualize in 3 dimensions, make sure you look at the book or at some source so you can get a sense of what these things actually look like and how to do those. For instance, if you have this book, they kind of show like what some of the different shapes would look like as they're added up, and so you can like get a sense of that a little bit better. All right. So that's polarity. Any other questions about that? As usual with these things, as I'm always saying, practice is key. There's only so many different shapes and different ways you can put these things together. So if you do a whole bunch of practice problems, you're going to see all the different ways of adding up vectors. You're going to get a chance to practice those. It's going to be fine. If you just say, okay, I think I kind of get how that works, and then don't try it again until it's quiz or exam time, it's probably not going to work out well for you. All right, on to our next big topic here. Valence bond theory. So recall that in the Lewis model, what we just talked about, we said that electrons like to get paired up and make bonds to satisfy octets. And that kind of works to give us some molecular structures. Man, this thing really wants to reboot, huh? But it doesn't work for other stuff. And so we need a little bit more robust theory of what's actually going on, because what Lewis proposed really doesn't explain a lot of the phenomena that we see. As we'll also see, this idea of valence bond theory doesn't explain a lot either, or breaks down also, so we need an even more robust theory that we call molecular orbital theory, and we'll look at that next. But valence bond theory basically says that bonds occur from adjacent orbitals overlapping on molecules. So kind of the classic example, which is actually kind of an exception, is hydrogen. Let's take a look at a graph like this. So if you imagine 2 hydrogen atoms, each one has an electron in a 1s orbital. Again, we often think of orbitals as areas containing electrons. But really, remember, electrons are both particles and waves at the same time. So the orbital is actually a description of the electron itself, not just the area where the electron is. So if you have 2 1s electrons on 2 hydrogen atoms, as the hydrogen atoms get closer and closer together, the interaction energy between those orbitals stabilizes the molecules. And we call that a bond. So what you see here is the distance between the nuclei, the center of the nuclei, plotted in terms of energy, overall potential energy, or I guess it's total energy. So you've got, number 1, you've got 2 separate atoms that are basically at energy of 0. They get closer and closer and closer together. Their orbitals start to overlap. And at a particular point, you start to get a drop in energy. So around 2, they start to stabilize each other by being close. Around 3, they're at the most stable they can be. And then at 4, the energy starts to shoot up again. In hydrogen's case, it's because of the nuclei getting too close together now, and they're starting to repel each other. In other molecules, atoms and molecules, we have a bigger component from what we call the Pauli repulsion, because electrons can't occupy the same orbitals, they can't have the same quantum numbers. So as things get too close together, the electrons start to get in the same orbitals, and that's a problem. Start to overlap with other orbitals with the same quantum numbers. So what we call this a bond, this distance here that has the maximum stabilization based on that orbital overlap model. So using this idea, what we say then is that these bonds that we've been drawing, these lines, are not just electrons being paired up, but they're actually orbitals that have overlapped. And those overlapping orbitals are stabilizing the overall compound. Okay, so let's talk about where this kind of breaks down a little bit. Let's look at methane, CH4. So in CH4, if we use our skills that we've learned so far, we can draw a Lewis structure like this. I think we've drawn this one before. And then we also know now that it's not a square planar molecule like that, but its shape is actually tetrahedral. And just to kind of exaggerate the shape, I'm going to use a convention that we sometimes use where we draw a wedge-shaped bond to show that a bond is kind of coming out at you, and a dash-shaped bond to show that it's going back behind the board. So that just kind of accentuates the three-dimensional structure there. So this is a symmetric type structure. Like if those H's were something else like fluorine or chlorine, this would still be a nonpolar structure because everything is canceled out in all those directions. But if we go back down to the orbitals and use this assumption that we just made about how the orbitals overlap, this doesn't quite make sense. Because we know what the atomic orbitals on carbon look like. We've got a 2s orbital, the valence orbitals, right? If we imagine a carbon atom, there's a 2s orbital. Then there's two p orbitals that kind of go like this. We'll call that one the 2py. Call this one the 2px. And there'd be one kind of coming out and back, the 2pz. Those are the atomic orbitals on carbon in the carbon valence shell. We could say that there are electrons in the 2s and one electron each in two of the 2p's. Doesn't really matter which ones because we've got 4 total valence electrons. So that's all stuff we've done before. In no way does that kind of arrangement explain the actual shape that we see. Because if we said, okay, well, these things are caused by orbital overlap, then we run into a problem. I'm not going to try to draw it here, but I'll show you the picture. Let me make this a little bit bigger for you. So take a look at that picture. If we imagine hydrogen atoms interacting with the p orbitals, we know that p orbitals are perpendicular to each other. So if we say, okay, well, the hydrogens come in and the orbitals overlap, then we would expect to see a 90-degree bond angle. We would expect to see that flat bond angle. Furthermore, the bonding with the s electrons should be closer into the nucleus. So we would expect to see like 2 short bonds and 2 long bonds at roughly 90-degree angles. And that's not what we observe. We observe 4 equal bonds distributed around the center. So the valence bond theory has to be revised a little bit to account for that. To account for that observed reality, as they say. And the way that this has been described is with the concept called hybrid orbitals. And we say that the s and p orbitals hybridize or mix together to make new orbitals that are combinations of s and p atomic orbitals. These are still atomic orbitals. These are still orbitals that are on the atom. But instead of an s orbital or a p orbital, we have sp, sp2, and sp3 hybrid orbitals. So these are orbitals that are formed from an s orbital mixing with a certain number of p orbitals. Again, since we're working in 3 dimensions, these are a little bit hard to draw, although I'll give you some tips in a little bit. So let's just kind of look at the picture in the book. So here we've got our 4 atomic orbitals on the left, the s orbital and the 3 p orbitals. And if you mix those all together, you mix their components together, you get these things called sp3 orbitals, so made up of 1 s orbital and 3 p orbitals. So you combine all 4 of them together, you get sp3 orbitals. And if you actually do it mathematically, if you make combinations of those orbitals, you get these weird kind of shaped things that have a big lobe and a little lobe. And if you measure all the components properly, they do actually end up pointing to the corners of a tetrahedron, as would be expected. So this is a way to explain what's observed. This is a way to explain the observed shape by saying that these orbitals combine and hybridize. So this is a useful, often a useful way of explaining things, a useful justification, especially as we get into organic chemistry, where all this stuff behaves quite nicely. But it is also probably worth saying that this idea of hybridization is still controversial to a lot of people. It still doesn't do a great job of reflecting reality and reflecting what we really see. So it's another one of those examples of something that is useful in certain situations and with certain types of molecules, but is not necessarily like absolutely true. There's no way to look at, if you actually do electronic calculations and measurements on molecules, you don't really find hybrid orbitals. Hybrid orbitals are a justification for geometry, not really for actual electronic structure, so not really saying what the electrons are doing so much. All right, so that said, we can now kind of describe the bonding in a molecule like methane by saying that we have 4 of these hybridized sp3 orbitals that are now connecting with hydrogen atoms and doing the orbital overlap thing that we described earlier. And that actually works to explain what's going on here. Okay. So the key to finding the right type of hybridization, or to understanding the hybridization, is to recognize that hybridization comes from geometry. It's a way of justifying geometry. It's not like the geometry comes from the hybridization. So hybridization always goes with geometry. And I'm going to put always in quotes because, of course, it's chemistry, so stuff gets, there's exceptions and stuff. So for our purposes, we can make that assumption for now. So what do I mean by that? I mean that the number of hybrid orbitals is always going to correspond to the number of different bonds that you need, or the different groups that you need. So if you have 4 electron groups, you're going to get sp3 hybridization. Which is 4 hybrid sp3 orbitals. So your s and your 3p's are all going to hybridize to make 4 sp3 orbitals. And those orbitals are then used to overlap with whatever things are bonded, or to contain lone pairs. All right, so some examples of that. We just talked about methane. CH4, 4 groups, 4 orbitals, sp3 hybridization. Another example would be ammonia, NH3. 3 atoms, but 4 overall electron groups. Right? Again, 4 hybrid orbitals. 3 of them to bond with the hydrogens, and 1 to contain the lone pair. Water, another example. 4 electron groups, 4 hybrid orbitals. These are all examples of molecules that we would say, using this theory, has sp3 hybridization. Remember, it goes right along with geometry. You don't have to get into the theory behind it to figure out the hybridization, because the hybridization goes with the geometry. The hybridization is a theoretical justification for the observed geometry. All right, so then if we have fewer than 4 electron groups, we still have hybridization, but we don't need as many hybrid orbitals because we don't have as many things connected anymore. So the hybridization changes a little bit. If we have 3 electron groups, instead of sp3 hybridization, we have sp2 hybridization. So the s orbital hybridizes with 2 of the p orbitals, and what does that leave? If we're using 2 of the p orbitals to hybridize, that means we have a leftover, unused, unhybridized p orbital. So we end up with 3 sp2 orbitals plus 1 unhybridized p orbital. And then for 2 electron groups, we call that sp. Which is going to give us 2 sp orbitals and 2 leftover p orbitals. Again, goes right along with geometry. All right. So some of the consequences of this are that we can explain some slightly more complicated bonding schemes. To do that, we need to make a couple definitions. There are 2 ways that orbitals can overlap each other to make a bond. The first is called the sigma bond. And a sigma bond is kind of like what we saw in that hydrogen example, where 2 orbitals kind of just smash together. So we've got you could have 2 s orbitals, and they kind of smash together to make something like that. And that's our sigma bond. You can also have p orbitals do this if they're kind of on their sides. So anytime 2 orbitals kind of smash together, that's called a sigma bond. And then we can mix these up and do it with hybrid orbitals too. So you can have a, let's say an sp3 hybrid orbital and an s orbital from a hydrogen, and you end up with, something like that, and that's called a sigma bond between an sp3 and an s. So that's our basic bonding that we've been talking about. The orbitals smash together, and the atoms are connected in that way. But there's also a second way that orbitals can overlap. There's actually a third way as well, but we're not going to get into that in this class, called the pi bond. And this is when orbitals like p orbitals d orbitals can do this to some extent as well. Rather than lining up lobe to lobe and just sort of smashing together, they line up parallel, and they can interact that way as well. So in a pi bond, you can take two p orbitals that are parallel to each other, and you can make, hold on, try that again. You can make this kind of an interaction. Sorry, let me show you what that book calls that. It'll look a little bit better with their nice pictures. Maybe not. Yes, there it is. Okay. So you can see here now the two p orbitals can kind of smash together and make this pi bond, which is different from a sigma bond. It has a node in the middle, so an area of no electron density. And so when we have multiple bonding in molecules, one way that we can explain that is by saying that it is a sigma bond caused by the hybrid orbitals overlapping, and then a pi bond or multiple pi bonds caused by the extra unhybridized p orbitals overlapping. So let's take a look at how we would do that. So let's take a look at a structure like CH2O, formaldehyde. If we draw a Lewis structure for that and get the geometry and all that stuff, we come up with this. Oh, and lone pairs on the oxygen. All right, so this would be a trigonal planar structure, 3 groups. And so we can look at that middle carbon atom, and we can say that we would expect this carbon atom to exhibit sp2 hybridization because there are 3 electron groups, and we know that hybridization goes along with geometry. Okay. So there's our sp2 orbitals on that carbon. But we can also kind of zoom in on this and try to justify what's going on with the orbitals overlapping in this molecule based on that assumption that it's sp2 hybridization or hybridized. So I'm going to redraw this molecule kind of looking on edge. So if we're looking, remember this is a flat planar molecule, so let's kind of tip it and look at it from the edge. So if we were kind of looking at this on the edge, it might look something like that. See that? It's flat. Since we know that that carbon is sp2 hybridization or hybridized, we expect 3 hybrid sp2 orbitals kind of coming out from that carbon that point in the different directions of the other atoms based on the geometry that we've already described. So we've got one like this. So these are going to be sp2 orbitals. One going out toward the hydrogen, and one going out toward the other hydrogen. And remember, they have that little tiny bit on the other side. This is going to get a little messy, so I'll show you the nice picture from the book after we finish constructing it. We also, because of sp2 hybridization, that means we've only hybridized the s orbital and 2 of the p orbitals. So we still have an orbital left over. We have that third p orbital left over. And so we're going to draw it kind of sticking straight out of the carbon. Now remember, carbon has 4 valence electrons. So one way we can describe this bonding is saying that there's 1 electron in each of the sp2 hybrid orbitals, and then 1 electron in the p orbital that's unhybridized. And then we can think about how these orbitals interact with the orbitals on the other atoms. So hydrogen doesn't have any p orbitals. Hydrogen has s orbitals. Let's pick another color for that. So we can draw two hydrogen s orbitals like that and say that those bonds so that bond we can describe as a sigma bond between the hydrogen 1s orbital and the carbon sp2 hybrid orbital. The oxygen one is going to be a little bit different because oxygen has its valence electrons in p orbitals as well. So for the oxygen orbitals, it's actually, we can think of that as actually bonding with a p orbital. And then oxygen would also have, oxygen we're going to say is unhybridized because we usually only talk about hybridization on the central atoms, the interior atoms. I told you this was getting messy. So we have a couple different interactions now with oxygen. We have a sigma bond right here that goes between an sp2 on the carbon and a p orbital on the oxygen. And actually, oops, I forgot the atoms there. Let's put the atoms in there. So this is going to be our carbon sp2 and our oxygen p. But in our Lewis structure, we also drew a double bond. We drew two bonds between the carbon and the oxygen. So one way we can talk about that second bond, because we've only shown one bond here based on orbital overlap. So one way we can talk about that second bond is to say that there's a pi bond between the carbon and the oxygen, those remaining orbitals. So this would be our pi bond between the carbon p orbital and the oxygen p orbital. So that's how we use valence bond theory to describe the bonding in a compound. We find the geometry first, just like we did before. We find the Lewis structure, we find the geometry. Then we say, okay, well, if it's this geometry, it has to be this particular hybridization. And then we can draw in the hybrid orbitals and talk about which orbitals are mixing with which other orbitals. Any questions about that so far? All right, if we look at the nice pictures from the book, same molecule, we get something like this. I can copy this into our notes. Maybe. Computer lets me. I guess I should have restarted when it was angry at me. Oh, that's still the old one. All right, so there's our valence bond model of what's happening in that molecule. We've got carbon with its 3 hybrid orbitals given here in purple. Its sp2 orbitals. Those are each bonding with a hydrogen atom, the s orbital from a hydrogen atom, and then one of them is bonding with the p orbital from the oxygen to make those are all our sigma bonds. And then our pi bond is the carbon and the oxygen with their parallel p orbitals. If we count up the bonds in this molecule, which is one thing you need to do on your lab, so we've got a sigma bond here, a sigma bond here, a sigma bond here, and a pi bond here. So 3 sigma bonds and 1 pi bond. One thing that sometimes confuses people is because a pi bond has 2 lobes, kind of a top lobe and a bottom lobe, it looks like it should be 2 bonds, but that's all considered 1 bond. So a double bond is a sigma bond and a pi bond. It's that middle interaction and the top and bottom interaction. So the total number of sigma and pi bonds should be the same as whatever you drew in your Lewis structure. So we draw a Lewis structure like that. We've got 4 bonds. Then our valence bond description should also include 4 bonds. In this case, it's 3 sigma bonds and 1 pi bond. All right. So a couple other things about valence bond theory. One is we can extend this, again, to other types of molecules. Actually, that's not a great example. Let's not do that one. If we looked at C2H2, we would draw a Lewis structure like this. And now we've got a triple bond. So what do you think is going on here? Based on extending our ideas from valence bond theory, how do we describe a triple bond? Any guesses? So we won't go through and do the whole thing, but we can look at the book again and look at their nice pictures because it gets a little even messier. In a triple bond, we have linear geometry. So we can think about each of these carbons now as having its own geometry, its own environment. And the second part of your lab says to draw some structures of some organic compounds. Those compounds now have multiple atoms that we might consider as central atoms. So we can no longer just say this is the central atom. We can look at each atom that has stuff connected to it that's not on the very outside and think about that. So each of these carbons, we would say, has 2 electron groups, and therefore what kind of geometry? Linear geometry and sp hybridization. Yep. So each of these carbons is going to have linear geometry and sp hybridization. That means that they will have 2 hybrid orbitals that will be responsible for the sigma bonds connecting the 2 carbons and the carbons to the hydrogens. And then there will be unhybridized p orbitals sticking out from the carbon in 2 different directions. And those will be the pi bonds that give rise to the double and triple parts of the bond. So that looks like this. There's our Lewis structure. We've got our carbons with, again, purple sp hybrid orbitals. One of the hybrid orbitals here bonding with the hydrogen, and then the 2 hybrid orbitals bonding together to make a sigma bond between carbons. And then we've got our 2 pi bonds, one in that same kind of vertical direction that we saw with the previous structure, and then there's another one perpendicular to that from the other p orbitals kind of coming out at you. All right. So the last part of this, I don't even really want to write in the notes because I don't like it. I'll tell you why I don't like it. But it is in the book. And that is, okay, how do we deal with these compounds that have more than an octet? What do we do with something like PF3 or SF6 or whatever, these big compounds that have 5 or 6 different bonds? Because none of the stuff we just talked about explains that. There aren't enough orbitals. So Lewis is, well, actually, I think this is after Lewis. I think this was Linus Pauling's description, maybe. Said, okay, well, we'll just continue, and we'll say that the third row and below have d orbitals, so we can hybridize the d orbitals, and that explains our expanded bonding. So instead of having sp, sp2, and sp3, we can add the d orbitals and have sp3d and sp3d2. This is one of those things that kind of is taught all the time, year after year, but there's never really been any evidence for it. There's no evidence of d-orbital hybridization. It's purely a justification for the observed molecular geometry, but there's really no evidence saying that it's the correct theory. It's an interesting idea. It kind of fits, and it works nicely from like a pattern standpoint, which is why you see it in textbooks. But realistically, there's no evidence that d orbitals can really participate in these in this sort of bonding. And the reason for that is that d orbitals lie much higher in energy. Remember, we kind of fill those other things, and then we have these d orbitals that are way up high in energy. So the idea that those d orbitals would be significant contributors to this bonding and to this hybridization is a little bit sketchy, I think. So I'm not gonna. I don't feel comfortable as a chemist saying that you should know about sp3d and sp3d2 hybridization, but it is in the homework. It is a common thing that's like taught in this thing. It won't be on the exam. It won't be on the final, but you might encounter it. And if you want to feel smart, or just be one of those people, if someone's telling you about sp3d hybridization, you can be like, it's not real. And you can come talk to me about it, and I'll give you some references if you like to fight with people about stuff like that. All right. So, putting all of this together, something like what we have seen on, or what you see on the homework, the lab homework, is a really nice way of thinking about this, because these ideas can seem very disconnected, but they're actually all ways of talking about the same thing. So you've got electron geometry, you've got molecular geometry, you've got bond angles, you've got hybridization. All of those go together. So if you've got 4 electron groups, you've got tetrahedral geometry, you've got around 110-degree bond angles, you've got sp3 hybridization, and you've got either tetrahedral, trigonal pyramidal, or bent molecular geometry. So it all goes together. Then you go to the next line and talk about 3 electron groups, or talk about 2 electron groups, or 5 electron groups. It all goes together. Right? So that said, let's use our last couple minutes to just briefly talk about the bigger molecules that you see in your homework, or that you may see in your homework. And we'll maybe work on this a little bit downstairs too if we run out of time. So the lab So now you should be well equipped to do part A. We know you knew those first 4 before, but now you can also determine hybridization, number of sigma bonds, pi bonds, and whether it's polar or nonpolar by adding up those vectors. That basically sums up what we've done so far, and that's what you should be able to do. Where this gets applied a little bit and kind of helps you get ready for future chemistry classes is in these bigger molecules. In these bigger molecules, we're not just looking at a central atom. We're kind of branching it out a little bit and trying to figure out what's going on each individual atom that's inside the molecule. So let's work on one together. Let's look at B. Which is C2H5OH. So a couple things you see about this that's a little different. One is the atoms aren't all collected together. One of the H's is listed over on the right instead of in with everything else. And that's because in these bigger compounds, because there's lots of different ways of making them, it's often really helpful to actually write the formula kind of spread out a little bit more, what we call a condensed formula, so that we can say something about how things are connected. So if we see a formula like this, we can assume that kind of the right side of this molecule, there's going to be an O and then an H, rather than having to figure all that out ourselves. So these more expanded formulas give us a little bit of a hint. So when I write a structure for this, because I see this over on the right, I can kind of make the assumption that, okay, there's going to be an O connected to an H, and then that's going to be connected to the rest of the stuff, because there's a reason that was split out. So then I have to come up with this C2H5 thing. Does that mean that I can do this? Well, let's say I did 5 of them. Is that a good starting place for my structure? You should see some problems with this. Anybody see a problem with this? What's the problem? Yeah, we can't have more than one bond on a hydrogen because it doesn't have enough electrons. Right? It's just got that one s. That one electron and that one s, it's only going to make one bond. So we can't really put hydrogens in the middle of stuff. So that's not going to work. And that actually ends up leading us to the real structure, because the only other choice we have then is to put carbons there. Now we also know that carbon has to have an octet, right? So that kind of gives us a clue as to where to put the rest of those hydrogens. And then if we add up all the electrons like normal, we'll also find 2 lone pairs to put on the oxygen to fulfill its octet. The nice thing about these organic structures is they're very predictable. In these structures, carbon will always have 4 bonds. Oxygen will pretty much always have 2. Hydrogen will have 1. So it makes it a little bit easier to write. But now that we know all this other stuff, we want to think more about the geometry and the hybridization going on in here too. So even though we drew this nice and straight like our typical Lewis structure, we should recognize that, in fact, these would not be straight. What would be the geometry around those 3 internal atoms? What would the carbons be? Geometry-wise. Those carbons should each have tetrahedral geometry because they have 4 different things attached to them. You see that? 4 groups attached. So those would be tetrahedral. And what about the oxygen? Yeah, the electron geometry would also be tetrahedral, which means the molecular geometry would end up being bent. So we could redraw this if we want. I don't think that it asks you to on the lab, but we could better approximate those types of angles by drawing more of a kind of a bent structure like this that shows that 3-dimensionality a little bit more. And because we figured out the geometry of each of those carbons and oxygens, we've also figured out the hybridization. What's the hybridization on all of those? They've all got to be sp3, because anything that is tetrahedral is sp3 hybridized. All right? That's it for now. I'll see you downstairs, and we'll practice this some more.